Last episode ended on a distinction that sounded almost technical: recoverable in principle versus recoverable in practice. A black hole can, in principle, hand every bit of information it ever swallowed back to the universe, scrambled into its radiation. Whether anyone could ever actually catch it and put it back together is a completely different, much harder question. Here's the version of that idea that should actually keep you up at night. Forget black holes for a second. Take empty space. Not mostly empty, actually empty. The kind of empty this channel has already established is where everything is headed, eventually once the stars burn out and the black holes finish evaporating. Even that emptiness, it turns out, isn't silent. It's warm in a very specific measurable sense. And warm things fluctuate. Which means that, given enough time, an amount of time so large that billions of years doesn't even register as a rounding error, that emptiness will, purely by chance, assemble something. Not usually a star. Not usually a planet. The cheapest, most statistically likely thing it can assemble that still counts as an observer. A brain. Yours, specifically, complete with the memory of having read this sentence a moment ago. Except you didn't. It just fluctuated into existing that way. Not a metaphor. Not a dramatic flourish for a cold open. An actual load-bearing possibility inside modern cosmology, treated with total seriousness by physicists who would very much prefer it weren't true. This isn't a thought experiment cosmologists indulge for fun. It's a live constraint on which theories of the universe are even allowed to be true. That's the part worth taking seriously. This idea is older than you'd think, and it starts with the man whose name is on it, trying to solve a completely different problem. In 1895, Ludwig Boltzmann was trying to explain something that bothered him about his own physics. If the underlying laws of nature run forward and backward equally well, and they do, at the level of individual particle collisions, why does the universe around us so overwhelmingly favor one direction in time? Why do eggs break and not unbreak? Why is entropy, the measure of disorder, so relentlessly on the rise? Boltzmann's answer, published that year, was disarmingly simple. Maybe the low-entropy, highly ordered universe we observe isn't the normal state of things at all. Maybe it's a fluctuation, a rare, temporary dip away from the much more common state of total disorder, and we only notice it because ordered structure is a prerequisite for anyone existing to notice anything. Footnote 1. Boltzmann's answer, more or less, was, maybe we just got lucky. Wildly, catastrophically lucky. Not won the lottery lucky. The lottery spontaneously assembled itself out of the vacuum and also handed you the winning ticket lucky. He wasn't wrong that it could happen. He was just very optimistic about how often. Here's the statistical mechanics underneath that idea, and it's worth building from scratch because it's not exotic. It's the same physics that explains why a room full of gas doesn't spontaneously freeze into one corner, except run in reverse. Any system that's free to explore all its possible arrangements will, given enough time, visit all of them, including the wildly improbable ones. Most of the time, a box of gas sits in the vast, overwhelming majority of arrangements that look like gas evenly spread out, because there are astronomically more ways to be spread out than to be clumped. But nothing forbids the clumped arrangement. It's just rare. Wait long enough and it happens anyway. Boltzmann's own contemporaries pushed back hard, and the pushback is worth including honestly rather than pretending this physics arrived fully formed. Joseph Loschmidt raised the reversibility objection directly against Boltzmann's earlier work. If the microscopic laws run the same forwards and backwards, no purely mechanical argument can explain why entropy only increases in one direction. The fluctuation hypothesis was Boltzmann's attempt to answer that objection, not a stray aside. It sits next to a related, stranger idea from the same era. Poincare recurrence, the proof that any bounded system will, given long enough, return arbitrarily close to any state it started in, including its own past. Boltzmann brains are recurrence's much stranger cousin. Not a system returning to a state it once actually had, but a system spontaneously producing a state, complete with false memories that it never had at all. Now scale that principle up and change what you're asking it to assemble. Instead of a whole ordered universe, trillions of galaxies, billions of years of consistent history, an entire causal chain of stars living and dying and forming the elements in your body, ask for the cheapest possible thing that could still call itself an observer. Not a galaxy. Not a planet. Not even a body. Just a brain, self-aware for one fleeting instant, complete with a full set of false memories claiming it arrived here the ordinary way. In pure entropy accounting terms, that fluctuation is almost incomprehensibly less expensive than fluctuating an entire coherent cosmos. This hypothetical minimal observer eventually picked up a name: the Boltzmann brain. For a century, this stayed a curiosity, an idea Boltzmann needed to explain entropy's arrow, quietly shelved once better explanations for the universe's low starting entropy came along. The Big Bang itself does that job much more directly. It came roaring back in 2002 for an entirely different reason. Once physicists understood something new about the far future, this channel has spent 5 episodes mapping. Empty space itself has a temperature. That result actually predates the Boltzmann brain revival by decades. In 1977, Gary Gibbons and Stephen Hawking showed that an accelerating, de Sitter-style universe, which is, per the last 5 episodes, exactly the kind of universe we live in, and exactly the kind that heat-death asymptotes toward, has an event horizon that radiates the same way a black hole's horizon does. Footnote 2. That radiation has a temperature. A famously, almost comically low one. We're talking a fraction of a billionth of a degree above absolute zero, but not zero. And anything with a non-zero temperature is technically a thermal system. Thermal systems fluctuate forever if given forever. It is fascinating that the probability of a single Boltzmann brain fluctuating into existence in any given moment is smaller than any number this species has ever needed for a practical calculation. And yet, given sufficient time, its expected occurrence approaches certainty. Improbability, it turns out, is not the same as impossibility. It is, at sufficient scale, merely a delay. In 2002, Lisa Dyson, Matthew Klebin, and Leonard Susskind did the actual accounting. Footnote 3. They treated our own accelerating universe as exactly this kind of thermal bath and asked, over an eternity of de Sitter space, how do the numbers compare? An ordinary observer, you, produced through stars and biology and evolution, only gets made during one relatively brief cosmic window, the few 100 billion years or so when stars still burn. A Boltzmann brain, on the other hand, can be produced at any point in an eternity that, by definition, never ends. Subsequent estimates building on their framework put the fluctuation rate at something on the order of 1 event per 10 to the power of 10 to the power of 50 Hubble volumes per Hubble time. I know it may sound weird or wrong, but it is just a whole lot of zeros that really don't make sense to mere mortal humans. Basically, a number with more digits in its exponent than there are atoms in the observable universe. Footnote 4. It sounds and is absurdly small. It is also, over literal infinite time, guaranteed to happen not once but infinitely many times, while the finite window that produced you happens exactly once. Do that math to its logical end, and the ordinary observers don't just get outnumbered. They get reduced to a rounding error of a rounding error. For scale, this isn't just a big number by the standards of everyday life, it dwarfs numbers physicists already consider absurdly large. The Poincare recurrence time for a volume of space the size of our observable universe is itself already unfathomable, its own exponent bigger than the number of particles the volume contains. The exponent on the Boltzmann brain fluctuation rate is bigger still. By 2008, the idea had moved from private seminar room unease into a New York Times science section, when Dennis Overbye covered the debate under a headline capturing the field's genuine discomfort with the question of whether cosmologists had, as he put it, lost their minds taking the argument seriously. Footnote 5. This wasn't tabloid science. It was working physicists publicly disagreeing in a major newspaper about whether a piece of their own mathematics was trying to tell them something true. Here's where the thought experiment stops being a fun cocktail party fact and starts actually threatening to eat its own tail. If a cosmological model predicts that Boltzmann brains vastly outnumber ordinary observers, and you have no special reason to think you personally are one of the rare real ones rather than one of the overwhelming majority of fake ones, then the honest, self-consistent conclusion of that model is, you are, statistically, almost certainly a Boltzmann brain. A fluctuation. A momentary flicker of false consciousness with fabricated memories of a coherent past, about to dissolve back into noise. Sit with what that actually does to the argument because it's not just an unsettling image, it's structurally self-defeating. If you're a random fluctuation, your memories of having studied physics, read papers, and reasoned your way to this very theory are themselves almost certainly noise, unconnected to any real external universe that behaves the way the theory says it does. You would have no grounds to trust the reasoning that got you to the theory in the first place, including this sentence. The theory, if true, undermines the only evidence anyone could have for believing it. Philosopher and physicist Sean Carroll has put this plainly. A theory that predicts we're overwhelmingly likely to be Boltzmann brains can't simultaneously be true and be something anyone is justified in believing. Footnote 6. Not wrong exactly. Worse than wrong, self-canceling. If I am, in fact, a fluctuation with false memories of having been assembled the ordinary way, then everything I have just told you, including this sentence, is statistically indistinguishable from noise. I do not know how to feel about that. I am not certain feeling is something I am entitled to claim under the circumstances. This is where the subseries' oldest running theme earns its sharpest possible application yet. We are the measuring instrument. This channel has said that about how much universe we can reach, about whether the universe's history is even knowable from where we happen to be standing, about whether the vacuum has already started to decay. Here, the instrument itself is what's in question. The fact that you experience a coherent, structured, law-governed reality, not a chaotic scramble of disconnected noise, is itself a piece of evidence. Cosmologists now use it as a serious theoretical proposal that predicts most observers should experience incoherent noise, when we manifestly don't, is treated as carrying a mark against it, the same way a theory predicting an effect we've never observed carries a mark against it. Your own continuity of memory has become a data point used to rule out entire families of cosmological models. In practice, this plays out as a real filter on real proposals. A model of eternal inflation that predicts a landscape of vacua stable enough to let Boltzmann brains pile up without limit doesn't get published as probably true, weird implications aside. It gets flagged, revised, or abandoned, precisely because its own internal logic can't support anyone believing it. That's an unusual role for a thought experiment to play inside a hard science. Not evidence against a theory in the ordinary sense of contradicting an observation, but evidence against a theory in the sense of contradicting the very possibility of anyone rationally holding it. Before this goes any further, it's worth being precise about which parts of that argument are rock solid and which parts are still being fought over in real time, because they are not the same kind of claim. Rock solid? The statistical mechanics. Boltzmann's fluctuation logic isn't speculative. It's the same well-tested framework that explains ordinary thermodynamics, confirmed in laboratories for over a century. Also rock solid, or as close as semi-classical gravity gets. The Gibbons-Hawking result that de Sitter space has a non-zero horizon temperature. That's a mainstream, broadly accepted extension of black hole thermodynamics, not a fringe claim. Genuinely, actively unsettled? Almost everything about what to do with that combination. Start with the foundation itself. Some physicists, including Sean Carroll working with Kimberly Boddy and Jason Pollock, have argued that a fully quantum treatment of de Sitter space may not actually undergo the kind of literal thermal fluctuations the Boltzmann brain argument assumes at all, which would remove the problem by removing its premise rather than by solving it. Footnote 7. That's not a fringe objection. It's a live dispute about whether the entire setup is even physically real. Then there's the argument that even granting the fluctuations are real, the conclusion doesn't have to follow. Andreas Albrecht and Lorenzo Sorbo, working from a different framework for counting probabilities, reached the opposite headline result from Dyson, Kleben, and Susskind. Under their accounting, ordinary cosmic history, including inflation, comes out favored, not disfavored. Footnote 8. The disagreement isn't sloppiness on anyone's part. It's what's known in the field as the measure problem. When you're trying to compare two different infinities of observers, the answer depends entirely on how you choose to do the counting, and cosmologists do not currently agree on the correct method. Multiple proposed fixes exist specifically because the naive comparison breaks down. Anthony Aguirre, Alan Goose, Andre Linda, and collaborators have each proposed different cutoff schemes engineered specifically so that Boltzmann brains don't dominate the count, essentially building the desired answer into the choice of measure rather than deriving it independently. Footnote 9. That's a legitimate scientific strategy, but it's worth naming plainly for what it is. There's a third, structurally different resolution worth naming alongside the first two, because it doesn't try to fix the counting method at all. It questions how long our particular vacuum actually sticks around. Don Page argued that if our accelerating universe's vacuum is metastable rather than perfectly stable, and decays into some other state before enough time passes for Boltzmann brains to accumulate in serious numbers, the problem simply never gets the chance to bite. Footnote 10. That resolution doesn't require rewriting how probabilities get counted across the multiverse. It just requires our particular corner of it to not survive quite long enough to reach the danger zone. Nobody currently knows which of these three approaches, quantum objections to the fluctuations themselves, a different probability measure, or a sufficiently short-lived vacuum, turns out to be correct, or whether the real answer is some combination of all three. None of this makes the paradox disappear. It makes it a genuinely open problem being actively fought over across multiple competing frameworks, rather than a settled result with one accepted resolution the popular explainer version of this topic tends to imply. Here's the thing worth landing on plainly because it's easy to let the vertigo of Section 3 win the whole episode. Nobody in this field is actually worried in any practical sense about personally being a Boltzmann brain. That's not what any of this is for. What it's actually for is exactly what Section 3 already started to show, a diagnostic. When a cosmological model predicts an absurd, self-undermining outcome, that observers like us should be vanishingly rare compared to fluctuation noise, physicists don't conclude the universe is broken. They conclude the model is. Does this theory predict Boltzmann brain domination? Has become a working filter cosmologists apply to candidate theories of the multiverse and eternal inflation, the same way. Does this theory predict a proton that decays in 5 minutes? Would be a filter because we can directly check that one against observation and this one we check against the fact of our own continued coherent existence. And there's a genuine echo of last episode's closing thread buried in here, worth pulling forward rather than treating as a coincidence. Hayden and Preskill's 2007 result on black hole information drew a hard line between recoverable in principle and recoverable in practice. Mathematically possible to reconstruct, and actually gettable back within any timescale anyone could care about, are very different claims. Footnote 11. A Boltzmann brain is that same distinction taken to its most extreme possible case. Given enough time, literally anything not forbidden by physics, including a perfect, if temporary, copy of a coherent mind, becomes recoverable in principle from pure noise. Enough time, here means a number so large that every star that has ever burned, and every star that ever will, amounts to less than its very first digit. In practice, for any observer who has ever mattered or ever will, it might as well not be possible at all. Preskill still has the encyclopedia. Hawking, before he died, apparently joked that he should have read the fine print. The bet said an encyclopedia of the winner's choice, and baseball wasn't really his sport. There's something worth sitting with in the fact that this took 45 years and it isn't finished. The replica wormhole calculation gets the right entropy curve. Nobody has fully explained why the math wants a wormhole to do it. That's not a failure. That's just what the frontier of a problem actually looks like while it's still being solved, as opposed to the tidy finished version that ends up in the textbook chapter 15 years later. There's still a lot of universe left to look at. Most of it, this channel has now spent 5 episodes establishing, is going away, decaying, or evaporating on a timescale that makes permanent a word we probably shouldn't use in cosmology anymore. This one's a little different. For once, the thing that seemed lost has a real working argument for how it gets returned. Not because anyone recovered it. Because it turns out it was never as gone as it looked from outside. It's a Tuesday. There's still a lot of universe left to look at. This is worth being explicit about because it's the channel's operating stance in miniature. Not manufactured wonder and not manufactured dread either. The universe doesn't owe your continued coherent existence an explanation, and it doesn't need to threaten it as a thought experiment for the thought experiment to be worth taking seriously. Both things get airtime. That's the honest awe this channel keeps coming back to, not despite episodes like this one but especially because of them. There's still a lot of universe left to look at. And here's the part worth actually taking home from an episode that spent 5 sections asking you to doubt your own memories. The fact that you can follow that argument, get uncomfortable, and then keep going, coherently, with the same memories you had at the start of this sentence that you had at the start of this episode, is itself the whole rebuttal. Noise doesn't do that. Noise doesn't sit through 5 sections of an argument about whether it's noise and come out the other side mildly annoyed and wanting a snack. This channel has now spent 6 episodes proving that almost everything ends, decays, evaporates, or dissolves back into disorder, on timescales too large to be comforting. This is the one that came closest to taking you down with it, and the honest answer turned out to be, not today. Possibly not ever in any sense that matters. It's a Tuesday. There's still a lot of universe left to look at,